Well, in these videos, I will talk about carbohydrate chemistry. This term is very much familiar to all of us, and we all intake this every day. If you are not a superstar like Shah Rukh Khan, Amitabh Bachchan, Deepika Padukone, or Katrina Kaif, then I think you also intake this every day. I thought that this chapter is so small that it will take 1 or 2 weeks to complete, but it took almost 1 month to complete all these aspects. So I will make 4 or 5 videos which have in total 360 slides. Go through these all videos and I am pretty much sure that you all will learn a lot of things. So let's begin the carbohydrate chemistry. Carbohydrates, which mean hydrates of carbon. These carbohydrates are substances with the general formula CxH2OY, where X and Y are integers. We encounter carbohydrates at almost every turn of our daily lives. Paper, cotton of our clothes, the wood of our houses, the flour from which we make bread is mainly starch. And starch is also a major constituent of many other foodstuffs, such as potatoes, rice, beans, corn, and peas. Carbohydrates are central to metabolism, and they are important for cell recognition. So this is the percentage composition of honey. Honey mainly contains more than 70% of carbohydrate. Fructose, it contains 38.2% fructose, 31% glucose. This portion is of fructose, 38.2. This one is of glucose, 31%. And this portion corresponds to water, which is 17.1%. And some other carbohydrates, maltose, and some other higher carbohydrates are also present in honey. So if you are learning something, I prefer to learn from the top to bottom. That means মাথার চুল থেকে পায়ের নখ অবধি সবকিছুই জানা উচিত. That's why I will start with the Fischer projection, which is very much important in carbohydrate chemistry. Fischer projection. This is actually the Fischer projection of a molecule, and I will tell you that how to present it. This is the eclipsed form of the molecule, and you are viewing this molecule from this side. Then your eye will see this kind of thing, and in the Fischer projection you will get this one. Let me describe this. You are watching from this angle. This bond and this bond, these are in the back of the plane. This is your reference plane, and this two and this two, these 4 atoms are in front of the plane. So you will see a structure like this. Your eye will see this, and if you just project it on a paper, you will get the Fischer projection. Now the appropriate method of writing these structures, that the higher oxidized carbon atom should be placed at the top and the lower one should be at the bottom. The numbering will also start from the top. Now see that this one is CHO aldehyde group and this one is CH2OH group. As the CHO group is the higher oxidized carbon, that's why we are numbering it as 1 and writing is at the top. The next one will be 2, this carbon will be 3, and this will be 4. Okay. The following 5 rules summarize the conventions used in the construction of Fischer projections. Number 1. A Fischer projection is based on an eclipsed molecular conformation. 2. The bonds connecting the asymmetric carbons are arranged in a vertical line. 3. The asymmetric carbons are located at the intersections of vertical and horizontal bonds and are not drawn explicitly. 4. Vertical bonds to the asymmetric carbons recede behind the page, away from the observer in the three-dimensional model. 5. Horizontal bonds to the asymmetric carbons emerge from the page toward the observer in the three-dimensional model. Now this is the eclipsed conformation of a molecule and how to derive a Fischer projection for D-glucose. Okay, this is D-glucose, structure of D-glucose, open ring structure. This A is the open ring structure of D-glucose, the naturally occurring enantiomer. Now first, the eclipsed conformation is viewed with the chain of carbons oriented vertically and curving away from the observer, and the horizontal bonds projecting towards the observer. This view is projected onto an imaginary curved cylinder. This is your imaginary curved cylinder, and you are just projecting this molecule onto the surface of this cylinder. Now mentally cutting the cylinder and flattening it gives the Fischer projection. So if you project this molecule on a cylinder, curved cylinder, and then cut it along this direction and then flat it, then you will get this Fischer projection. The use of an eclipsed conformation to derive a Fischer projection does not mean that the molecule actually has such a conformation. Fischer projections convey no information about molecular conformations. Their only purpose is to show the absolute configuration of each asymmetric carbon. To derive a three-dimensional model of a molecule from its Fischer projection, reverse the process. The vertical bonds in the Fischer projection extend away from the observer and the horizontal bonds extend toward the observer. So you have to just reverse the process. You have got this Fischer projection and you are getting an eclipsed conformation of the molecule. This vertical bond, this one and this one, will be away from the observer. These two, which are away from the observer, you are viewing from this molecule, this side, and these the horizontal bonds, these are towards the observer. That means here one is in the front, another is in the back, but these two are in the upside from which you are viewing this molecule. A Fischer projection may be turned 180 degree in the plane of the paper. This manipulation is allowed because it leaves horizontal bonds horizontal and vertical bonds vertical. Therefore, it does not alter the meaning of the Fischer projection. So, if you have a Fischer projection, then you can turn it 180 degree in the paper. So, this top carbon will go to the bottom and this bottom carbon will come to the top. This is Fischer allowed. A Fischer projection may not be turned 90 degree in the plane of the page. So if you have a Fischer projection, you cannot rotate it 90 degree in the plane of the page, because now this were your vertical bond, now this have become the horizontal bond, which is forbidden. So go through the lines. This manipulation violates the Fischer convention that all asymmetric carbons should be aligned vertically. When we attempt this operation on a Fischer projection containing a single asymmetric carbon, a further problem becomes evident. Now here we have a single asymmetric carbon. Now if we rotate this Fischer projection 90 degree on the plane of the page, then you will actually get an enantiomer of the first molecule. So you are finally getting this, which is an enantiomer of the first molecule. The 90 degree rotation exchanges horizontal and vertical groups, and in the process interconverts the original structure into the enantiomer. This is disastrous because the whole idea of Fischer projections is to convey stereochemical information. A Fischer projection may not be lifted from the plane of the paper and turned over. So you cannot take it from the plane of the paper and you cannot turn it. This is forbidden in the Fischer projection. Otherwise you will get an enantiomer. If you just put it from the paper and then turn it 180 degree, you will get an enantiomer. And an enantiomer is actually a mirror image of this previous one. This one is the mirror, although it's not looking like a mirror, but just consider that this is a mirror. So you will get an mirror image in this case, and that will be an enantiomer. The three groups at either end of a Fischer projection may be interchanged in a cyclic permutation. That is, all three groups can be moved at the same time in a closed loop so that each occupies an adjacent position. Yes, this is very much important thing in case of Fischer projection, that you can rotate this, you can interchange the positions in a cyclic manner. That means you can take this AH here, this OH here, and this CH2OH here. This is Fischer allowed. So all the conformations will be same in case of this one and this one. If this center was R, here also this will be R in case of RS nomenclature. Now in case of this, you can also just make a cyclic permutation here or even here. An interchange of any two of the groups bound to an asymmetric carbon changes the configuration of that carbon. A pair of interchanges leaves the configuration of the carbon unaffected. The first interchange changes the configuration, and the second interchange changes the configuration back to the original. That means if you change these two groups, this H and OH, if you make a change, you will get the enantiomer of this molecule. But if you make two consecutive change, then you will get the same isomer. The RS system can be applied to a Fischer projection without using a model. If the group of lowest priority is in either of the two vertical positions, simply apply the RS priority rules to the remaining three groups. You know that in case of RS nomenclature, you have to number all the 4 atoms connected with the asymmetric carbon, and you have to do it by CIP rules, Kahn in gold prelog rules. And the lowest priority group, if in case of Fischer projection this is in a vertical position, then you can just apply the RS or CIP rule on the other three priority atoms. Now in case of 1, 2, 3, you are getting anti-clockwise rotation. That means this will give S. Anti-clockwise or counterclockwise rotation, you can say. This will lead to an S enantiomer. This method works because if the lowest priority group is in a vertical position in the Fischer projection, it is oriented away from the observer as required for application of the priority rules. If the lowest priority group is in a horizontal position, proceed in the same manner, but since the molecule is being viewed incorrectly for assigning configuration, reverse the assignment. That means if your least prior group is in a horizontal position and not in a vertical position, then just go to the cyclic manner 1 2 3 1 2 3. This is giving a clockwise rotation, but as this least prior group is in a horizontal position, you have to take it reverse. So if you got the clockwise, you have to consider the counterclockwise rotation, and this will lead to S. Now this is a homework for all of you, that you have to indicate whether the structures in each of the following pairs are enantiomer or diastereomer or identical molecules. Okay, I can help you that at first that take this CH3 in this vertical position and this CH3 in this vertical position. Then actually you will get that these two are identical molecules. This one and this one identical. And in case of this one, just simply rotate it 180 degree on the plane of the paper. So you will get this. Now the next question is, which of the following are Fischer projections of a meso compound? So I am giving a hint that if you have to find out a meso compound, then you have to find out a plane of symmetry. That means in this case this will be the plane of the symmetry. So this, you don't have to consider this asymmetric carbon because this will go to the plane of the symmetry. And in the first case this is a CHO and this is CH2OH, so this is definitely not. In the second case this will be a meso compound. In third and fourth these will also be not, but you have to check this C and D. Make an interchange with the CH2OH and H group, then you will see that these are not meso compounds. D and L designations of monosaccharides. This is capital D and this is capital L. Don't be confused with the small d and small l, which are actually for the optical rotation, which denotes the optical rotation, dextrorotatory and levorotatory. The DL system, named after Latin dexter and levus, which means right and left, is a convention used to distinguish between enantiomers of chiral monosaccharides and chiral alpha-amino acids, based on the molecule drawn as a Fischer projection in a specific orientation. The DL leveling is unrelated to plus minus. It does not indicate which enantiomer is dextrorotatory and which is levorotatory. Rather, it indicates the compound's stereochemistry. If the prior group of the highest number of asymmetric carbon is in the right, that will be the D configuration, and if the prior group is in the left, that will be the L configuration. Early in the 20th century, before the absolute configurations of any organic compounds were known, this system of stereochemical designations was introduced. According to this system, which was first suggested by M. A. Rozanoff in 1906, plus glyceraldehyde is designated as D-glyceraldehyde and minus glyceraldehyde is designated as L-glyceraldehyde. These two compounds moreover served as configurational standards for all monosaccharides. A monosaccharide whose highest numbered chirality center has the same configuration as D-glyceraldehyde is designated as D-sugar. One whose highest numbered chirality center has the same configuration as L-glyceraldehyde is designated as an L-sugar. And it has a disadvantage that it specifies only the configuration of one chirality center, that is the highest numbered chirality center, and other chirality centers are not described by this D or L system. To determine whether a given enantiomer of a chiral monosaccharide is D or L, use the following procedure. Step 1. Make sure the acyclic form of the molecule is drawn as a Fischer projection. If the monosaccharide is an aldose, the aldehyde group must be on top. If it is a ketose, the carbonyl carbon must be the second carbon from the top. Step 2. Number the carbon atoms starting at the top. Step 3. Locate the carbon atom that bears the second highest number, which is known as the penultimate carbon. That means which is the highest asymmetric carbon. If the hydroxy group on the penultimate carbon is on the right of the carbon chain, assign the label D to that compound. If it is on the left of the carbon chain, assign label D. Now this is your penultimate carbon, that means highest numbered asymmetric carbon, and the prior group OH is in the right side of this vertical bond. That's why this is D, and here the OH group in the highest numbered of asymmetric carbon, which is the penultimate carbon, is on the left side. That's why this is L. Now this is also a exercise for you. Classify each of the following aldoses as D or L. So I am giving you a hint that at first make a cyclic permutation here. So that's why CH3 will come in the vertical, OH will go to the horizontal, and H will go here, and you will get this is D. And you can just check the next one yourself, do it yourself. Okay, so this is a 10 seconds break. Let me drink some water. Now we will start the main course of the carbohydrate. Carbohydrates are usually defined as polyhydroxy aldehydes and ketones, or substances that hydrolyze to yield polyhydroxy aldehydes and ketones. They exist primarily in their hemiacetal or acetal forms. Simple carbohydrates are also known as sugars or saccharides. The Latin saccharum and Greek saccharon, which means sugar. And the ending of the names of most sugar is O's. This is the ending. At the ending you have to add O's. Thus we have such names as sucrose for ordinary table sugar, glucose for the principal sugar in blood, fructose for a sugar in fruits and honey, and maltose for malt sugar. You can see everywhere there is a O's suffix. Carbohydrates can be divided into 4 groups: monosaccharide, disaccharide, oligosaccharide, and polysaccharide. Actually, in many books you will find some different form, that in some book they are saying that it can be divided into 2 groups, you can say 3 groups, but I prefer to divide it into 4 groups: monosaccharide, disaccharide, oligosaccharide, and polysaccharide. Monosaccharide means which cannot be hydrolyzed. Disaccharide means which on hydrolysis will give you 2 sugars, and oligosaccharide, which means 4 to 10 sugar units. And polysaccharides actually contains a large number of sugar units. A carbohydrate containing an aldehyde group is called an aldose. One containing a keto group is called a ketose. A ketose can also be indicated with the suffix ulose. Thus, a 5-carbon ketose is called a pentulose. Now come to the branch monosaccharide. This is a huge branch, These are sugars which cannot be hydrolyzed into smaller molecules. Their general formula is CnH2nON. The simplest monosaccharide is glycolaldehyde. This is the simplest one with 2 carbon atoms. This does not contain any asymmetric carbon atom, thus optically inactive. Since all naturally occurring sugars are optically active, it is excluded from the group of sugar. So this is the simplest carbohydrate, but this is not a sugar because it is optically inactive. Glyceraldehyde is an aldotriose. It contains one asymmetric carbon atom and therefore exists in 2 optically active forms. This is the D-glyceraldehyde and this is the L. Because this OH group, the more prior group is in the right, this is the D. And here the OH group is in the left, that's why this is the L. Dihydroxyacetone, this is the ketotriose. This is the youngest member of the keto group, dihydroxyacetone. Okay, now come to the aldotetrose. There are 2 asymmetric carbon in aldotetrose, thus 2 pair of enantiomer is possible. These are the aldotetrose, which have erythrose and triose. This is the D form, this is also D form, this is the L form, this is the L form. Actually this is a aldehyde group, 1 hydrogen. You should consider 1 hydrogen. Here is also 1 hydrogen. Don't think it a ketose, okay? This is aldose. Now ketotetrose. This is the ketotetrose, D-erythrulose. You can get also the L form. Aldopentose. Okay, so in case of aldopentose, there are 4 varieties. That means 4 pair. I have just shown the D-aldopentoses, D-ribose. This is the structure of D-ribose, D-arabinose, D-xylose, and D-lixose. So you have to just remember these OH groups. Where are they located? Here 1 is on the left, 2 on the right. So there is an easy way, I will tell you later. So you just note down all these structures. Now how to remember this? There is a process that you can remember from glyceraldehyde to lixose by this line. Go, Ernest, Thomas, ring Arabians xylophones loudly. Go means glyceraldehyde, Ernest comes from the erythrose, Thomas triose. Actually I prefer to write Thanos, not Thomas. I prefer to say go Ernest, Thanos, ring Arabians xylophones loudly. If you are a Marvel fan, then you must know who is Thanos. Ring, here ring means the ribose, Arabians mean the arabinos, xylophones corresponds to xylose, and loudly this corresponds to lixose. This is the short form by which you can remember all these. D-ribose occur in liver, pancreas, nucleic acid, and plant nucleic acid. So D-ribose is very important. Okay, these are the ketopentose. There are 2 pair of ketopentose. These 2 are the D forms. You can also get L forms. This is the D-ribulose. This one is the D-ribulose. This one is the D-xylulose. Now this is the aldohexose family. Starts with allose, altrose, glucose, mannose, and there are 4 others: glucose, idose, galactose, and talose. In total there are 8 pairs of enantiomers. in the aldohexose. How to remember this? This is the easiest form. All altruists gladly makes gum in gallon tanks. By remembering this, you can remember all the aldohexoses properly. And what does the altruist mean? Altruist is the person unselfishly concerned for the welfare of others. When I first heard this line, I couldn't understand the meaning of altruist because I am a Bengali medium student. That's why I couldn't understand this. So I thought that maybe some of you also can't understand. That's why I have written this meaning. Here all corresponds to allos, altruist, altrose, gladly, glucose, and so on. You can just see this. And there is another short form. Just go about this portion. What is it actually? If you have drawn all the structures, then you can see properly. Just try to understand the positions of the OH groups. I am going here. In case of allos, see that all 4 OH are in right hand side. That means all these 4s are in the same side. Now in case of altrose, the first one is on the left and the rest of the 3 are on the right. So you can generalize it in this way. For allos, the asymmetric carbons contain all the OH groups in the right hand side. That's why R. In case of altrose, the first one is on the left, the next 3 are on the right. So LR. This, in case of glucose, the first one is on the right, second one on the left, and the third and fourth are on the right. So by doing this, you can remember all the structures. And how to remember this formula? At first, draw this first line. RL in this direction. Just one after another, one after another. And in case of the second line, alter the RL after 2. RR, In the next line, the alteration will be after 4. RR, L. And in the last line, there will be no alteration. And if you just take the columns, you will get this allos, altrose, glucose, mannose, glucose, all of this. So try to remember in an easy way. These are the family of ketohexose, which contains psychose, fructose, sorbose, and tagatose. This also have the same form, that all the OH in psychose are in the right side. That's why this contains RR. In case of fructose, the first one is on the left and the other 2 on the right. That's why LRR. In sorbose, this is R. The first one is on the R, next one is on the left, right, third one is on the right. So RLR. And in tagatose, the first 2 are on the left and the next one is on the right. So LLR. So here is also the same trend will go on. At first, write RL like this, alteration after 1. In the next line, there will be alteration after 2, RR, LL. And in the third line, there will be no alteration, RR. So this is for the D family. If you want to get the L enantiomer, for instance, if you want to take the L fructose, you know the structure of the D fructose, just take the mirror image of this, you will get the L fructose. You get it? Now this is the family tree of the D series of aldoses. 3 to 6 carbon atoms. At first there is glyceraldehyde, then erythrose, triose, then ribose, arabinose, xylose, lixose, and thereafter allose, altrose, glucose, mannose, glucose, iodose, galactose, and talose. Now family tree of the D series of ketones, 4 to 6 carbon atoms. So the ketose, first optically active ketose is erythrulose, and then after you will get ribulose, xylulose, cyclose, fructose, sorbose, and tagatose. So write down all these structures. Now the question may arise that why D-glucose is the most abundant aldohexose in the nature? Because all the OH substituents in beta-D-glucose are equatorial. The axial positions are all occupied by hydrogens which require little space and therefore experience little steric strain. No other aldohexose exists in such strain-free conformation. Because of this, D-glucose is the most abundant aldohexose in nature. Oh, wow. 10 seconds break. Okay, I will not take 10 seconds. Now come to properties of aldohexoses. Molecular weight analysis show the formula is C6H12O6. When treated with red phosphorus and hydriodic acid at 100 degrees centigrade, these give N-hexane, which indicates that the 6 carbon atoms are in a straight chain. So if you take an aldohexose and if you treat with red phosphorus and hydriodic acid HI, you will get the N-hexane. The next one is that aldohexoses form an oxime when treated with hydroxylamine, which proves the presence of carbonyl group. So if you take this hydroxylamine, you will get an oxime. This NH2 will condense with this ketone group. I think you know the mechanism that the lone pairs of nitrogen will attack the carbon, then this bond will be opened. Then after a protonation occur, and then again this proton will leave, and again nitrogen will get a lone pair, then again it will attack the carbon, and then you will get this structure C-double-bond-N. Just try to do the mechanism yourself. If you can't do it, then comment below and I will put the mechanism. The fourth point is that when treated with acetic anhydride, aldohexoses form pentacetate. This proves the presence of 5 hydroxyl groups. So if you take acetic anhydride, then you will get pentasubstituted aldehyde. This proves that this aldohexose contains 5 hydroxyl groups. Actually, this mechanism also very easy, that if you have the OH, oxygen contains lone pair, this oxygen will attack this Ac2O and will become OSE. Actually these these oxygens are oxygens of this glucose. Bromine water can oxidize an aldohexose. That indicates that the carbonyl group is present as aldehyde group. Okay, remember that bromine water can't oxidize the ketones. That means it can't oxidize ketone group. Okay, it only can oxidize the aldehyde group. Points which proves that there is no free aldehyde. The first point is that it gives negative taste with Schiff's reagent. Second point is negative taste with sodium bisulfite. Third is only one equivalent alcohol is needed to complete acetal formation. However, that aldoses will combine with two molecules of a thiol to form a mercaptal. That means a thioacetal. So actually it takes one equivalent of alcohol. If it were in the free state, then it would take two equivalent of alcohol, which happens in the case of thiol. It consumes two molecules of thiol. But as it is not in the open chain form, that's why it takes only one equivalent alcohol to form acetal. That means it is actually in hemiacetal form. The fourth point is that it shows mutual rotation. The fifth is X-ray analysis definitely proves the existence of the ring structure and at the same time indicates the size of the ring. Cyclic structure of monosaccharides. Here I have shown the different kinds of representation of glucose molecule. So at first try to understand that this is your Fischer projection formula of glucose. This is the circle and line formula, and this is wedge line dashed wedge formula. And this is the Hart formula. These are the chair forms. These two are the chair forms. Then first go that how to convert a Fischer to Hart. You have to make a cyclic permutation here. You have to take the OH here, CH to OH will go there and hydrogen will come here. Then here was your OH. This oxygen will attack this aldehyde carbon from the back, and you will get another new asymmetric carbon. Now see this. This is your open chain glucose, and here there is a Fischer allowed rotation. You are just rotating this, and this OH will come here, CH to OH will go there, and this H will come here. So after this you will get this structure, the open chain form of D-glucose. The proton transfer step occurs between separate molecules. It is not intramolecular or concerted. Okay, you have to understand this, that this proton transfer is not concerted. Now what happens? This proton goes out, this oxygen attacks here, this oxygen becomes negative, O minus, and that O minus takes another proton. And for this, now this carbon has become an asymmetric center. It can orient itself in two manner. That means this OH can be in the back side or OH can be in the front or in the upper side. So if this OH is in the opposite side of this CH2OH, that's why this is the alpha D glucose. This is said alpha because this OH is in the opposite of this CH2OH, and here this OH is in the same side of this CH2OH. That's why it is said beta D glucopyranose. These ring structures are said pyranose, 6-member rings. I will tell it later. It is convenient to represent the cyclic structures of a monosaccharide without specifying whether the configuration of the anomeric carbon atom is alpha or beta. That means for our convenience we just write it as this without specifying whether it is an alpha or beta. This is the Hart form, this is the chair form. If the monosaccharide ring is 6-membered, the compound is called a pyranose. This is the form of the pyran. From this pyran you are getting the term pyranose, because the ring is a six-membered ring. If the ring is five-membered, the compound is designated as a furanose. This is the structure of furan. And if you get a five-membered ring, that will be a furanose. In many carbohydrates, both 5 and 6-membered cyclic hemiacetals are possible, depending on which hydroxy group undergoes cyclization. Yes, if you take an aldehyde form, you can get a furanose form and a pyranose form. If this OH attacks the carbonyl group, you will get a pyranose form. If this OH attacks the carbonyl group, you will get a furanose form. How can cyclic hemiacetal forms of carbohydrates be named according to their 5 or 6-membered rings? So how to make a name? To name a cyclic hemiacetal form of a carbohydrate, one has to start with a prefix derived from the name of the carbohydrate. For example, gluco for glucose, mano for mannose, followed by a suffix that indicates the type of hemiacetal ring. Pyranose for a 6-membered ring and furanose for a 5-membered ring. That means you have to do a prefix plus a suffix. The prefix will come from the structure of the sugar, from the name of the sugar, and the suffix will come from the structure of the sugar, whether it is a pyranose or furanose ring. Thus, a 6-membered cyclic hemiacetal form of D-glucose is called D-glucopyranose. Gluco is the prefix and pyranose is the suffix. D-glucopyranose. A 5-membered cyclic hemiacetal form of D-ribose is called D-ribofuranose. Here ribo comes from the word ribose, that's why it is the prefix, and furanose, it is the suffix. Epimer and anomer. Diastereomers differing only one configuration of one carbon atom is called epimers. That means if you have two diastereomers which are differing only at the configuration of one carbon, that is epimer. Any two molecules differing in the stereochemistry of only one carbon atom. Now see the structure of inositol and epiinositol. Here you can see that this OH, if you just start naming with 1, this 2, so the OH group of the third carbon atom, here see 1, 2, 3, this is in the back, right? In case of inositol, this was in the front, and in case of epiinositol, this is in the back. That means there is only difference in the configuration of one carbon atom. That's why these are epimers. In carbohydrate chemistry, mannose is the C2 epimer and galactose is the C4 epimer of glucose. You must remember this. This is a very important thing that you can get in any kind of exam, this type of MCQ, that mannose is the C2 epimer and galactose is the C4 epimer of glucose. Now anomers. What is anomer? In carbohydrate chemistry, diastereomers differing only at the hemiacetal or acetal carbon are called anomers, and the hemiacetal or acetal carbon atom is called the anomeric carbon atom. This is your aldehyde group. This is the hemiacetal carbon. This is actually called anomeric carbon, and these two are the anomers, which forms after the ring closure. The furanose or pyranose form of a carbohydrate, sorry, what is happening? Yes, the furanose or pyranose form of a carbohydrate has one more asymmetric carbon than the open chain form. Here you can see that in the open chain form there were only 4 asymmetric carbons. This 2, 3, 4 and 5. But in case of the chain structure, the one number of carbon is also an asymmetric carbon. So in case of this, In case of the ring closure, you can get 5 asymmetric carbons. Thus, there are 2 possible diastereomers of D-glucopyranose. So you will get extra 2 structures. That means if the OH is in the right side, you will get 1 anomer. If the OH is the left side, you will get another anomer. Actually, if the OH is in the right side, that is the alpha anomer, and if the OH is in the left side, that is the beta anomer. Okay, so which one is alpha and which one is the beta anomer? Okay, you have to understand this very carefully. In Fischer projection, the anomer in which the hemiacetal OH group is on the same side as the oxygen atom at the configurational carbon is called alpha anomer. That means if the hemiacetal OH is in the same side of this oxygen, which is the oxygen atom of the what can I say, this is the oxygen atom which is forming the ring. If these two are in the same side, that will give you alpha anomer. And now see that in this case the OH is in the one side and this O is another side. That's why this is the beta form. This oxygen is making the ring. This oxygen and the number 1 asymmetric carbon attached to oxygen is on the opposite side. That's why this is the beta anomer. This is for the case of Fischer projection. Now come in case of Haworth projection. The anomer in which the hemiacetal OH group is in the opposite side of the CH2OH group of the configurational carbon is alpha anomer. This is your anomeric carbon, this is your configurational carbon. So OH group and this CH2OH group are in the different position. That's why this is the alpha anomer. And here the anomeric carbon, and this is the OH group, here the configurational carbon, and this is the CH2OH group. These two groups are in the same side. That's why this is the beta anomer. In case of Haworth projection, you have to see this. Now in case of chair form, the anomer in which the hemiacetal OH is in the axial position while the CH2OH group is in the equatorial is called the alpha anomer. So if the OH group, anomeric OH group, is in the axial position, not only that, this CH2OH group have to be in the equatorial. This will be alpha, because if you just make a ring flip, this CH2OH will go in the axial, and then you cannot say this, that if the OH is also in the axial, then that will alpha. That will actually be then beta. Now you see that if you just do a ring flip, this CH2OH and this OH, both of them will go to the axial position. That will be beta, because in this case when CH2OH group, which you have to keep fixed at the equatorial position, if CH2OH group is in the equatorial, and then if the OH group, anomeric OH, is also in the equatorial, that will give you the beta anomer. This is the line and wedge structure. You can check that this will be the beta anomer. This is the beta, and this is the anomeric carbon. You can see this one is the anomeric carbon. This is the chain formation of alpha D glucose. This is the D glucose. You are getting alpha D glucose and beta D glucose from this open chain structure. And in case of D fructose, similarly you are getting alpha D fructose and beta D fructose. Just take a look. In case of alpha D glucose, the OH is in the opposite side of this CH2OH. In case of beta D glucose, the anomeric OH is in the same side of this CH2OH. Similarly, in case of fructose, you will see that actually here in case of fructose, you will see that this OH is in the different side and this CH2OH, both of group are in the same side. and in the beta D fructose both CH2OH is in the trans position, that means in the opposite phase. That's why this is the beta, and where the two CH2OH are in the same side, that one is the alpha. Now come to a short description of Haworth's projection. This is actually your D-glucose, the ring form of your D-glucose. You are just making a Fischer rotation in this manner. So your oxygen will come here, your CH2OH will come here, and this oxygen is attacking this carbonyl group from the back. So this is your ring form. Now if it is folded around a barrel or drum, such an interpretation of the Fischer projection of beta D glucopyranose yields the following structure. Actually I have made a mistake, this will be the capital D, not the small d. So if you take this, you will get this structure in case of Haworth's projection. And if you just make 90 degree, that means if you flat this, you will get this structure, where you can see this anomeric OH is in the same position of this CH2OH. So it will be beta anomer of D-glucose. When the plane of the ring is turned 90 degree so that the anomeric carbon is on the right and the ring oxygen is in the rear, the groups in up positions are those that are on the left in the Fischer projections. Now see again that in case of the Fischer projection, which groups are in the left? These groups, if these are in the left, these will be in the up position of this Haworth projection. You can see the first OH is on the left, here the OH is on the left, then the third OH is on the left, here the third OH is also on the upper side, and here CH2OH is on the left, so CH2OH is also in the upper side. So this is very closely related to the Fischer projection. You can get the Haworth projection from the Fischer projection. First make the ring closer and then just turn it 90 degree. Whereas the groups in down positions are those that are on the right in the Fischer projection. A planar structure of this sort is called a Haworth projection. In a Haworth projection, the ring is drawn in a plane perpendicular to the page and the positions of the substituents are indicated with up or down bonds. The wedged bonds are in front of the page and the others are in the back. So this is in front of you, and these groups OH, CH2OH, these two groups are in the upside. Okay, this OH, OH and CH2OH. So if you take line weight structure, you have to make them in bold. Okay, bold structure, OH, OH and CH2OH. And you are obviously just watching this molecule from this direction. That's why these three structures, these three positions are in front of your eyes, and this OH, OH are in back of your eye. That's why this OH will be dashed. Now again you are getting a Fischer projection of D-glucose, then you are making a Fischer rotation in this manner, then this OH is attacking this carbon and the bond is being opened. So again you can rotate the C1 C2 bond. That means if you rotate this bond, the carbonyl will go down, and if now this oxygen attacks, the OH will be in the back, that means in the down position. And now in this case, if the OH attacks, the OH will be in the up position. That means this is the beta D glucopyranose and this is the alpha D glucopyranose. Look again and try to understand this. In case of D fructose, the same thing happens, that take the Fischer projection of D fructose, make like this structure, and now take a cyclic permutation. After that, if this OH attacks this carbonyl group, you will get this structure, which is the alpha D fructofuranose. And if this 2,3 bonds rotates, this 2,3 bond rotates, so you will get actually this structure where the C11O is in the upside. So if now the oxygen attacks the carbon, the OH will be in the upside. The OH is in the upside. So in this case you will get the beta D fructofuranose. Okay, 10-second break for me. Now this is a very important concept, mutarotation. Mutarotation is the change in the optical rotation because of the change in the equilibrium between two anomers. Mutarotation was first discovered by French chemist Fort in 1844, when he noticed that the specific rotation of aqueous sugar solution changes with time. A solution of ordinary D-glucose, which has the melting point 146 degrees centigrade, has an initial specific rotation of 112 degree, but ultimately the specific rotation of this solution falls to 52.7 degree. This also must be a plus. You cannot indicate a specific rotation by only the value. You have to give the sign also, plus or minus. A solution of the second form of D-glucose, which has the melting point 150 degrees centigrade, has an initial specific rotation of plus 18.7 degree. But slowly the specific rotation of this solution rises to plus 52.7 degree. That means if you take the alpha D glucopyranose, which has the optical rotation plus 112 degree, or if you take the beta D glucopyranose, which has an optical rotation plus 18.7 degree, both will give this, not this, sorry, both will give the optical rotation as 52.7 degree. That means something is happening which are converting these two into one another. This change in specific rotation toward an equilibrium value is called mutarotation. Now I have shown a chart where you can see in case of glucose, in case of equilibrium, the alpha contains 36% and beta form has 64%. That means in equilibrium 36% alpha and 64% beta anomer is present. In case of galactose, there are 27 to 36% alpha anomer and 64 to 73% beta anomer, and different values for allose, altrose, iodose. You can see this all thing you can check. Now mechanism for the acid catalyzed mutarotation. If you give acid, it can show mutarotation. Now what is the mechanism? You are giving acid, means H3O plus. Now if this oxygen will take the proton, and this oxygen will be, the ring oxygen will be protonated first, then a open chain form will occur. This bond is being broken. Okay, just give me 1 second. Okay, this bond is being opened and you are getting the open form, this one. Now this open form is in equilibrium. That means this can show rotation. So if it rotates, then you will get both the alpha and beta form. If it rotates in this way, if this bond rotates, you will get this one after rotation, and after the ring closure you will get this form. That means if you started with alpha D-glucopyranose and you are getting beta D-glucopyranose via a rotation of bonds. Now see very carefully what is happening here. At first this oxygen is taking the proton, then the ring is being broken, after then a rotation is occurring, then this oxygen is making ring again, and this OH leaves, then you are getting the beta D glucopyranose structure. This proton leaves, after the deprotonation you are getting beta D glucopyranose. Mechanism for the base catalyzed mutual rotation. Now if you give base, in case of basic medium there is also mutual rotation possible. At first this OH will take this OH from the base, will take this proton which is in the anomeric OH. The base will take this proton, so this oxygen will become minus, and after that the oxygen will give the electron in this CO bond, then this bond will be broken. Okay, this bond will break, and after that you will get a open ring structure. Now again a rotation can occur in this bond, a rotation can occur, and after rotation the carbonyl group which was in the bottom will go in the top, that means in the upper side, and this hydrogen will come here after the rotation. Now if this oxygen attacks here, the OH will group form here, that means O minus. Actually it is in the basic condition, that's why this will form O minus, not OH. And after the protonation, or if you add some water, this O minus will take a proton from here, and then you will get the beta D glucopyranose structure. So again alpha to beta in case of base catalyzed mutual rotation. Now mechanism for the acid base catalyzed mutual rotation. If you add both acid and base, their mutual rotation is possible. At first what you are doing, at first this is taking this water is taking the hydrogen. Now here the acid base means you are taking water which can act as acid as well as it can act as a base. So water is taking this hydrogen at first, so this is becoming O minus, this O minus is attacking, and this bond is being broken. After the bond being broken, this oxygen is taking a proton from the water. Try to understand this. Then the bond is being rotated, this O ketone group is going in the up, and this OH group is going in the down. Then again this oxygen is giving its lone pair here, attacking the carbonyl group, and you are getting beta D glucopyranose. Do these all reactions, draw these all, and try to understand. The absorption spectra in aqueous solution indicate the presence of open chain forms. According to Lowry, mutual rotation is not possible without the presence of an amphiprotic solvent, that is, a solvent which can function both as an acid and a base, such as water. Thus, Lowry and Faulkner showed the mutual rotation is arrested in pyridine solution, which is actually basic solution, and in cresol solution, which is the acidic solvent. But it takes place in the mixture of pyridine and cresol. So if you take individually the pyridine or cresol, that will not show the mutual rotation. But if you take a mixture of pyridine and cresol, that will show the mutual rotation. Let's see the mechanism in the presence of pyridine and phenol. So you have taken pyridine and phenol in the same mixture, reaction mixture, and you are also taking alpha D glucopyranose. So what will happen? The pyridine is a base, so at first the base will attack this anomeric OH and will take up this proton. So this oxygen will become the minus, then this minus charge will give its electron to the C and O bonding. That means it will make C double bond O. This bond will be broken. This bond will be broken, and this O will immediately take a proton from this phenol. So you will get this open structure, open ring structure, and again there is a possibility of bond rotation. So if this bond rotates, this carbon will go in the top, this hydrogen will go in the bottom. Now again this phenol, that means the conjugate base of this phenol, will take proton from this OH. That means this is the phenoxide ion. This phenoxide will take a proton. This oxygen will become minus. This minus will attack this carbonyl. This minus will attack the carbonyl, and this will open. So this oxygen will take this proton from the pyridinium salt. Then you will get the beta D glucopyranose. I hope you can understand this reaction mechanism. Now the mutual rotation is also possible in case of 2-pyridinol. Since 2-pyridinol is an acid-base catalyst that gives proton to the acetal oxygen while removing H+ from anomeric hydroxyl group in a synchronous manner, mutual rotation occurs readily in the presence of 2-pyridinol. In case of 2-pyridinol, at first this nitrogen lone pair will attack this anomeric OH and take up a proton. Then this OH bond will be broken. This oxygen minus will give its electron to this C single bond O, and it will make C double bond O. So simultaneously this bond will be broken, and this oxygen will take a proton from this OH group of the 2-pyridinol. So all of these things are happening simultaneously. Then কি পাচ্ছি, আরে কি পাচ্ছি রে বাবা, then আমরা open chain ফর্মটা পাচ্ছি. That means we are getting this open chain form. তারপর কি হচ্ছে, তারপর বন্ডটা রোটেশন হচ্ছে, এই বন্ডটা ঘুরে যাচ্ছে, and उसके बाद क्या हो रहा है, उसके बाद this oxygen, actually this is taking the proton from here, ये ऑक्सीजन माइनस हो रहा है, अब ये माइनस इसे अटैक कर रहा है, और उसके बाद ये कार्बोनिल ग्रुप का भी, कार्बोनिल ग्रुप इस प्रोटॉन को ले रहा है. अब मेरा हिंदी बहुत ख़राब है, my Hindi is very bad, that's why I have to speak in English a little bit better, I hope so. So similarly you are getting this beta D glucopyranose. This is actually all the case of mutual rotation. If you take alpha anomer, you will get a mixture of alpha and beta, and if you take a beta anomer, you also will get a mixture of alpha and beta. So this is the actual funda of mutual rotation. When beta D fructopyranose, which has an initial specific rotation of minus 133.5 degree, is dissolved in water, it undergoes rapid mutual rotation to minus 92 degree. ओके सो आप दिस बीटा डी फ्रुक्टोपाइरानोज को ले रहे हो और उसके बाद म्यूटर रोटेशन हो रहा है और ऑप्टिकल रोटेशन जो है वो कम रही है, मतलब कम हो गया है. दिस म्यूटर रोटेशन इन्वॉल्व्स इक्विलिब्रेशन टू बोथ पायरानोज एंड फ्यूरानोज फॉर्म्स. ओहो क्या हो रहा है यहाँ, पायरानोज और फ्यूरानोज दोनों फॉर्म ही एग्जिस्ट कर रहा है. तो ये है आपका डी फ्रुक्टोज and you are taking beta D fructopyranose. At first this is converting into the open chain structure, then into the alpha D fructopyranose, as well as you are getting the fructofuranose alpha and beta D fructofuranose structure. So you are getting all these structures together, and you can see these percentages. Beta D fructopyranose has the 57% contribution, whereas the beta D fructofuranose has 31%, and these alphas are 9% and 3% in equilibrium. The NMR spectroscopy has been one of the primary techniques that chemists have used to determine the ratios of the various forms of monosaccharides in solution. Since the two pyranose forms are diastereomers, we could expect them to have different proton NMR spectra. However, since they are in equilibrium with each other, an NMR sample of D-glucose will contain both forms and peaks from each will be seen. ओहो ये तो बहुत ही मतलब इम्पोर्टेंट चीज़ है, बहुत ही गुरुत्वपूर्ण. सॉरी क्या हिंदी तो नहीं है, ये बंगाली ही हो गया. এটা খুবই গুরুত্বপূর্ণ জিনিস. তো কি হচ্ছে এই আলফা অ্যানোমারের হাইড্রোজেনটা, দিস ইজ giving peak at delta is equal to 5.21 ppm. so ये सब तो NMR का है डाटा. I will discuss it later if I make any video on NMR, but now I am just telling it in brief. This proton will give the delta value 5.21 and this proton will be at the delta value 4.63, and the J here, J is the coupling constant, the coupling between this 1H and the 2H. The coupling constant is greater for the beta anomer. In case of beta anomer, the coupling constant have the value 7.9 Hz, whereas the alpha anomer has the value 3.8 Hz. So try to remember this all in case of mutual rotation. The concentration of open chain D-glucose in solution at equilibrium is very small. Solutions of D-glucose give no observable UV or IR absorption band for a carbonyl group, and solution of D-glucose give a negative taste with Schiff's reagent, a special reagent that requires a relatively high concentration of a free aldehyde group rather than a hemiacetal in order to give a positive taste. Assuming that the concentration of the open chain form is negligible, one can, by use of the specific rotations in the preceding figures, calculate the percentages of the alpha and beta anomers present at equilibrium. These percentages comes out to be 36% alpha anomer and 64% beta anomer. These are in accord with a greater stability for beta D glucopyranose. As the beta D glucopyranose is much more stable than the alpha anomer, that's why it has the higher percentage. The beta anomer of a pyranose is not always the more stable. However, with D manose, the equilibrium favors the alpha anomer. So in case of glucose, you can see that beta D glucopyranose has the higher stability. That's why it is 64% at equilibrium and the alpha is 36%. But in case of manose, beta D manopyranose has the 31%, but the alpha D here, this one is the more stable, which has 69% in the equilibrium, because this OH and this OH are in trans, whereas this OH, these two fields some repulsion between them. Determination of the percentages of alpha and beta anomers of glucose present at the equilibrium. So let the mole fraction of alpha anomer is A and the mole fraction of beta anomer is B. Since the rotation of the mixture is plus 52.7 degree, we can write that the sum that we have the A fraction beta D glucopyranose. So A into 112 plus B into 18.7 will give this 52.7. A fraction, okay, this is not actually 36 or 64. This will be the fraction smaller than 1. There is very little of the open chain form present, so the fraction present as the alpha and beta anomer should account for all the glucose. That means we are neglecting the open chain form, and that's why we are getting a relation A plus B is equal to 1. The alpha D and beta D will contain all the glucose in case of equilibrium. We are assuming that, and then we are substituting B by 1 minus A. So we get this, and after a very short calculation, you all can do it yourself. You will get that the A will come out to be 0.36 and B will come out to be 0.64. So therefore at equilibrium the amounts of alpha anomer is 36% and beta anomer is 64%. How the two anomers of glucose can be separated? This is a big question, that how you can separate these two anomers. When glucose is crystallized from water at room temperature, pure crystalline alpha D glucopyranose is obtained, and when glucose is crystallized from water, letting the water evaporate at a temperature greater than 98 degrees centigrade, crystals of pure beta D glucopyranose are obtained. Anomeric effect. This is also called Edwards-Lemaitre effect. The term anomeric effect was introduced in 1958. This effect was originally observed in pyranose rings by J.T. Edward in 1955 while studying carbohydrate chemistry. The anomeric effect is most often observed with oxygen but can also be seen with other lone pair bearing heteroatoms in the ring, such as nitrogen, sulfur, and phosphorus. The preference for the axial position by an electronegative substituent such as alkoxy or acyloxy group bounded to the anomeric carbon is called the anomeric effect. For example, when D-glucose reacts with methanol in the presence of HCl to form a glucoside, the major product is methyl alpha D glucopyranoside with the OCH3 on C1 at the axial position, and the minor product is the methyl beta D glucopyranoside with the OCH3 group on the C1 at the equatorial position. This indicates that the alpha glucoside is thermodynamically more stable than the beta glucoside. Although conformationally, the beta anomer should be more stable. Now see, this is the structure of methyl alpha D glucopyranoside, where this OCH3 group is in the axial position. This is becoming more stable, and here in case of methyl beta D glucopyranoside, this OCH3 is in the equatorial and this is the less stable. You can say that their oxygen's lone pairs are actually there is some repulsion between these lone pairs. Actually, there are some beautiful logic behind this phenomenon. The first point is repulsion between non-bonding electrons. The dipoles associated with the non-bonding electrons of the alkoxy group at C1 and the non-bonding electrons on the oxygen atom of the ring repel each other when the alkoxy is in the equatorial position. That means these two lone pairs are repulsing each other. They are further apart when the alkoxy group is in the axial position. Because of this repulsive dipole-dipole interaction, the beta ionomer is thermodynamically less stable than the alpha ionomer, and as a consequence, the alpha ionomer is obtained as the major product. This is one reason. Another one is the hyperconjugation. A widely accepted explanation is that there is a stabilizing interaction, which is the hyperconjugation, between the unshared electron pair on the heteroatom, the endocyclic one in a sugar ring, and the sigma star orbital for the axial CX bond. That means there is some hyperconjugation from this oxygen lone pair to the sigma star of this carbon and oxygen. This causes the molecule to align the donating lone pair of electrons anti-parallel to the sigma star orbital, lowering the overall energy of the system and causing more stability. That means this orbital and this CX bond is in anti-parallel position, which gives more chance for the overlap. In case of this one, in case of this beta position, this is not anti-parallel. Here is sigma star and this one is the lone pair. These two are not anti-parallel. Even this one is also not anti-parallel with this. This cannot overlap. Another one reason is dipole minimization. Another explanation for the anomeric effect is the equatorial configuration has the dipoles involving both heteroatoms partially aligned and therefore repelling each other. By contrast, the axial configuration has these dipoles roughly opposing, thus representing a more stable and lower energy state. As the dipole, this one and this one is almost opposing each other, that's why this structure is more stable. But this dipole has a direction in this one is this. These dipoles vectors are repelling each other. They can repel. Now come to some effects. The first one is substitution effect or the substituent effect. When X, where X is the exocyclic group, is OH or CN, the equatorial position is preferred on the cyclohexane ring, but the axial position is preferred on the tetrahydropyran ring. That means if this is just a cyclohexane ring, this like this, then the equatorial position is preferred, this one. But if that is a tetrahydropyran ring, that means what is happening here? This one will be oxygen. If like a tetrahydropyran ring, then the axial position will be preferred, and this is X. When X is equal to fluorine, the anomeric effect is in fact observed for both rings. In case of fluorine, here in case of cyclohexane ring, fluorine will adopt the axial position. And in case of NH2, the no anomeric effect stabilization is observed for, and both systems prefer the equatorial position. If the X is NH2, then in both cases, that in case of cyclohexane and in case of tetrahydrofuran ring, in both case NH2 will adopt this this equatorial position. This is because of both steric and reverse anomeric effect. So we will learn what is the reverse anomeric effect after 1-2 minutes. Now see the solvent effect. A polar solvent with a high dielectric constant decreases the dipole-dipole repulsive interactions. The anomeric effect weakens as the polarity of the solvent increases, and as a result, the equilibrium is shifted in the direction of the conformationally more stable beta anomer. In a relatively less polar solvent such as methanol, the anomeric effect becomes much strong, and as a result, the amount of the alpha anomer increases. In fact, there is 50% of alpha D glucose in dry methanol. For a substituted tetrahydropyran, when X is equal to a fluorine, the anomeric effect was observed in both media. In the gas phase, that is with no solvent, and in aqueous solution, that is with polar solvent, the axial position was always preferred in case of fluorine. This is attributed to hyperconjugation. When X is OH hydroxyl group or CN, the anomeric effect was seen in the gas phase when the axial position was preferred. However, in aqueous solution, substituents prefers the equatorial position. So, in one case, the substituents are preferring axial, and in case of aqueous solution, the substituents are preferring equatorial position. But in case of NH2 group, no anomeric effect was observed and the equatorial position was always preferred. Some other factors. A substituent is more stable in the equatorial position because there is less steric strain in that position. The OH group bounded to the anomeric carbon is in the equatorial position in beta-D glucopyranose, whereas it is in the axial position in alpha-D glucopyranose. Again, the anomeric effect is outweighed by other factors such as an equatorial OH group is less crowded and better solvated by water than an axial one. This effect stabilizes the beta-pyranose form in aqueous solution. Also, the attractive interaction of the hydrogen of the anomeric OH group with the lone pair electrons of the ring oxygen decreases the importance of the anomeric effect, making beta-D glucopyranose more stable than the alpha anomer. For these reasons, beta-D glucopyranose predominates at equilibrium in an aqueous solution. Now, reverse anomeric effect. It refers to the apparent preference of positively charged nitrogen substituents for the equatorial conformation beyond what normal steric interactions would predict in rings containing an electronegative atom, such as oxygen. Substituents containing carbons with partial positive charges are not seen to exhibit the same effect. So what is happening in case of reverse anomeric effect? The substituent is preferring to be in the equatorial position. The pyridinium substituent strongly prefers the equatorial position, as steric factors would predict. That means it prefers more than the steric factors can predict, okay? But actually shows a stronger preference for this conformation than predicted, suggesting the reverse anomeric effect is contributing. So in case of this pyridinium type of salt, the reverse anomeric effect is much more pronounced.